This is the Russian scientist that first thought to lay out all the known atoms in order, and what he did is he wrote down a bunch of characteristics of the atoms. For example, he kept track of their density and their mass and melting points and what they look like. And this was the first sketch over here of what the periodic table might have looked, what his first thought of what the periodic table might look like. Well, it turned out that when he first arranged the periodic table, what he did is he actually picked one of those characteristics that we have listed here, and he arranged them by atomic mass. Now remember, the mass is the bottom number on the periodic table. And when he did that, he discovered a pattern. About every 8th element on the periodic table, when they were organized by mass, shared some sort of common characteristic, the way they reacted with other atoms, etc. Only thing being is it didn't always quite work. More on that in a minute. But most of the time it worked pretty good. Once he had it arranged in this pattern you see here, his rearranged periodic table, so what he did is he put question marks next to atoms that had not been discovered yet, but he predicted that they would be there because there were holes in the periodic table, things that he thought should be there but weren't based on the pattern. And so he even named them, as far as I know, predicted their properties, and sure enough, we later discovered those elements, and turns out that his predictions were pretty close to accurate. Now, like I said, there were some gaps in his pattern. It didn't always work, and that was because he arranged the periodic table by mass. A little later on, a guy named Moseley said, hey, let's arrange it by atomic number, which is really the number of protons. And when he did that, all the patterns fit. There were no gaps anymore in the patterns in the periodic table, and that's how our modern periodic table has been arranged. Here's the modern periodic table found in your textbook or anywhere online. And what I'm going to do is I'm just going to talk about some different arrangements and trends that we see in the periodic table. First thing students like to ask is about these atoms down here that have been pulled out. And basically we just pulled them out of this area right here to squeeze the periodic table into a smaller distance. So that's why those are down there. We really don't do much in terms of chemistry with those, so I won't talk much about them, at least in middle school chemistry. Next thing you'll notice, and if you've been in my class, we've already sort of discussed what you find on the periodic table in terms of this. I like this periodic table because if you look at the chemical symbol right here, you'll see that they've been color coordinated. So for example, all of these colors here are solids. So if you look at that, you see those are all solids. And liquids would be the blue and gases the green on the atomic symbol. The other thing you'll notice is there's 3 main categories that we find on the periodic table: metals, metalloids, nonmetals. And all the way from here over here we find the metals. Okay? And then along this line right here we find what are known as the metalloids, and they share characteristics of both. And then over here we find the nonmetals. Okay, first thing is period versus group. What's the difference between a period and a group? And you'll see that the periods go this way and groups go down this way. So if I talk about periods, you know I'm talking horizontal, groups talking vertical. Well, what we find if we move down the periods, so if we work our way down the periodic table this way, we find a common trend. The further you go down the periodic table, the atoms react with an increasing amount of energy. And you actually sort of already know the reason for this, as we've talked about in class. Atoms on the first period here, which is hydrogen and helium way across over here. Atoms on the first period, they only have one electron shell. And atoms in the second period have two shells. And atoms in the third period have three shells, etc. And the atoms keep getting bigger the further you go down. And so basically, as we talked about before, as you get further away from the nucleus, the electrons have more energy. And so when they interact with each other, it's the outer shell of electrons, or valence electrons, that react with the world. And so the further out you go, you get an increased amount of energy in the chemical reactions. Alright, well, what if we move across a left to right on the periodic table, or moving across the groups? And we did an activity in class where most of you discovered this, but it's worth just repeating. What we find is in group 1, we find that all the atoms have one valence electron. Group 2, we find that all the atoms have two valence electrons. And it gets a little fuzzy down here in these metals from here to here, groups 3 through 12. Most of these have 2 to 3 valence electrons. Okay? But we sort of skip that in terms of the pattern. If we keep cruising across over here to group 13, notice the second digit is a 3 in 13. They have 3 valence electrons. And over here in group 14, they have 4 valence electrons, 5 valence electrons, 6 valence electrons, 7 valence electrons. Helium has 2 valence electrons, and the rest of these have 8 valence electrons. So the pattern across the groups is valence electrons increases as you go left to right. Now, because of this pattern, what we find is that atoms in group 1, right here, their easiest way to become stable, and remember, stable means having a full outer shell or full set of valence electrons, is basically this group here wants to give up an electron. So for example, if, let's draw sodium from this group right here. If I drew sodium, it would have one valence electron on the outer shell. And on the other side over here, group 17 has 7 valence electrons. So let me draw a little chlorine over here. So chlorine would have 1, 2, 3, 4, 5, 6, 7. So the easiest way for chlorine to become stable is to add an electron, and that would make it have 8 electrons in its outer shell, making it stable. And sodium would just be happy to get rid of an electron, because remember, underneath of this extra outside electron is a full set of valence electrons. So underneath of the extra one is a full shell. That's exactly what we find happen, is this valence electron will fill chlorine's empty spot over here. And what that does is it puts a charge on sodium. So when this electron's no longer here anymore, it had 11 protons, and it used to have 11 electrons, but now it only has 10, and that puts a positive charge on sodium. And chlorine just gained an electron, and so chlorine had 17 protons, and now it has 18 electrons, so that puts a -1 charge on chlorine, and that makes these two atoms attracted to each other because they have a positive and negative charge, and they form what's called an ionic bond called sodium chloride, NaCl, sodium chloride. And now it's very stable. They're attracted to each other because they have a charge. And remember, sodium is a metal that reacts pretty violently with water. Chlorine's a gas that's pretty poisonous. Put these two things together and you get table salt. So it turns out that most of the things over here with group 1 will react with group 7, like I just said. This group has 2 extra valence electrons, group 2, so it tends to react with group 6 over here. Well, let's talk about the metals, metalloids and nonmetals, and we can actually see a pattern as you move from left to right on the periodic table with that, and it's pretty easy pattern to see. You'll notice that blues are the metals. Metalloids have characteristics in between metals and nonmetals are all the way on the right. It turns out as you move left to right, these items over here are very metallic in nature. In other words, they have very metallic-like characteristics, and it gets less and less so as you move over here until finally, how metallic the item is and acts gets less and less as you move left to right, and then pretty soon over here in the yellow, it's not metallic-like at all, and we call those things non-metals. So the groups in blue are the metals. The group in green called the metalloids, and these turn out to be really, really important in technology because they share characteristics of both metals and nonmetals. And one of the characteristics of metals, for example, is it's a good conductor. Metals are good conductors. That means that they can conduct heat good, and they also tend to conduct electricity really well. And nonmetals are just the opposite. They don't conduct heat very well, and they don't conduct electricity very well. So we use actually some of these, they're called semiconductors, in computers and stuff because we can actually, by temperature changes, we can make them sometimes conduct electricity and sometimes not conduct electricity. And so that's how we made circuits so small compared to the old type of circuits where you actually had to turn a switch on and off. I'm going to let you use your textbook to sort of research what are some of the properties of metals, what are some of the properties of these metalloids, and what are the properties of non-metals. All right, well, I hope that tutorial gives you some basics of the periodic table, and you can use that to help you fill out your Cornell notes, and along with this tutorial and your textbook should be plenty of help for you, and please feel free to see me if I missed anything. Thank you.